On July 1st, 2025, in the darkness of Chile's Rio Hurtado Valley, a telescope detected something that should not exist. Not in our solar system, not in our understanding of physics, not in the carefully constructed models we've built to explain the universe. The asteroid terrestrial-impact last alert system picked up a signal, a small dot of light moving against the cosmic backdrop. Within hours, astronomers knew they were looking at something unprecedented. Within days, they realized the laws of physics as we know them might be incomplete. They called it 3I Atlas, the third interstellar visitor ever confirmed in human history. But this was no ordinary cosmic traveler. This object arrived from the void between stars, traveling at speeds that defy conventional explanation, aligned at an angle that mathematics says is virtually impossible, and behaving in ways that have left the world's leading astrophysicists struggling for answers. Some whisper about natural phenomena we've never encountered. Others speak more cautiously, their voices dropping to hushed tones about possibilities that border on science fiction. What is 3I Atlas? Where did it come from? And why has one Harvard professor suggested that something beyond gravity, something we cannot yet explain, might be guiding its path through our solar system? The impossible discovery. The 20-inch telescope that first spotted 3I Atlas was designed to protect Earth. Its mission was simple: scan the night sky, identify asteroids that might threaten our planet, calculate their trajectories, and provide early warning. It had made thousands of discoveries since coming online in 2015. Routine observations, expected objects, nothing that challenged the fundamental laws of celestial mechanics. But on that July night, one of the Atlas telescopes locked onto something different. The object was moving, fast, too fast. Within 24 hours, astronomers around the world turned their instruments toward this mysterious visitor. They measured its speed, calculated its trajectory, and arrived at a conclusion that sent ripples through the scientific community. This object was not orbiting our sun. It was passing through our solar system at a staggering velocity of approximately 58 kilometers per second, faster than any previous interstellar object ever recorded. To understand what this means, consider that Earth orbits the Sun at roughly 30 kilometers per second. The fastest spacecraft humanity has ever built, the Parker Solar Probe, reaches speeds of about 190 kilometers per second at its closest approach to the Sun, but only because it's falling into the Sun's immense gravitational well. For an object to be traveling at 58 kilometers per second, far from any star, requires an origin beyond our solar system. It means this object has been journeying through the frozen void of interstellar space for billions of years, perhaps longer than Earth itself has existed. The Minor Planet Center in Cambridge, Massachusetts, collected 122 observations from 31 different observatories before making the official announcement. They designated it as 3I, marking it as the third confirmed interstellar object in recorded history. The previous two visitors, 1I Oumuamua in 2017 and 2I Borisov in 2019, had already challenged our understanding of the universe. But 3I Atlas was about to rewrite the textbooks entirely. The trajectory that defies probability. Space is vast, incomprehensibly vast. When we think of objects entering our solar system from interstellar space, we imagine them coming from any direction, above, below, from the sides, randomly oriented relative to the flat disk of planets that circle our sun. This disk, called the ecliptic plane, is where most of the major bodies in our solar system reside. The planets orbit within a few degrees of this plane because they all formed from the same spinning disk of gas and dust that surrounded the infant sun 4.5 billion years ago. Pluto, that distant world at the edge of our solar system, has an orbit tilted about 17 degrees from the ecliptic. Even this modest tilt makes Pluto unusual, a quirk that contributed to its eventual reclassification as a dwarf planet. When astronomers expect an interstellar object, something that has traveled light years through three-dimensional space with no connection to our solar system's formation, they expect it to arrive from a random angle. 3I Atlas arrived aligned within 5 degrees of the ecliptic plane. Let that sink in. An object that formed around a different star billions of years ago was ejected from that distant system, traveled through the vast emptiness between stars, and happened to intersect our solar system at almost exactly the same angle as the disk of planets that formed here. Professor Avi Loeb at Harvard University calculated the probability of such an alignment occurring by chance. His answer, 0.2%. Not impossible, but highly improbable. Statistically suspicious, the kind of number that makes scientists uncomfortable. Imagine shooting an arrow from one continent to another, across thousands of miles of ocean, and having it arrive perfectly parallel to the ground. That's the level of precision we're discussing. In three-dimensional space, with infinite possible angles of approach, 3i Atlas threaded the needle. It hit the bullseye, and nobody can quite explain why. Some scientists suggest it's simply a coincidence, a lucky roll of the cosmic dice. Others are not so sure. The alignment is so precise, so perfectly matched to the geometry of our solar system, that it raises uncomfortable questions. Questions that lead to even more uncomfortable answers. The hyperbolic nightmare. Every object in our solar system that orbits the sun follows a predictable path. Planets trace ellipses, returning to the same positions year after year, century after century. Comets from the Oort Cloud, that distant shell of icy bodies surrounding our solar system, also follow elliptical orbits, though some take thousands or millions of years to complete a single circuit. These orbits are described mathematically by their eccentricity, a number that tells us how elongated or circular the orbit is. A perfect circle has an eccentricity of 0. Earth's orbit has an eccentricity of about 0.017, nearly circular. Even the most elongated cometary orbits in our solar system rarely exceed eccentricities of 0.99. An eccentricity of exactly 1 represents a parabolic trajectory, the boundary between orbits that close on themselves and paths that escape to infinity. Anything greater than 1 is hyperbolic, meaning the object is moving too fast to be captured by the sun's gravity. It will pass through once and never return. 3i Atlas has an orbital eccentricity of 6.137. This is not just hyperbolic, this is extremely hyperbolic. So hyperbolic that its path through our solar system appears almost straight, barely curved by the sun's immense gravitational influence. For comparison, Oumuamua had an eccentricity of 1.2. Borisov's was 3.4. Both were clearly hyperbolic, clearly interstellar, clearly moving too fast to be bound to our sun. But 3i Atlas exceeds both by such a wide margin that it represents something new, something we've never seen before. Where does such velocity come from? How does an object achieve speeds that carry it between star systems in mere tens of thousands of years rather than millions? The answer lies in its origin, a stellar system that somehow imparted enormous kinetic energy to this object, flinging it into the void with enough momentum to cross the light years between stars. But the mechanics of such an ejection are not simple. It would require a close encounter with a massive planet, or a gravitational slingshot around a star, or perhaps something more exotic, something we haven't considered. Professor Avi Loeb, the Harvard astrophysicist who has become the public face of scientific speculation about 3i Atlas, suggested in a blog post that the object's trajectory shows signs of forces beyond simple gravity. He noted discrepancies between the comet's predicted position based on gravitational calculations and its observed location. These discrepancies suggest either that the object is far more massive than it appears, or that something else, something not accounted for in our models, is influencing its motion. The force we cannot name. Comets are not passive objects. When they approach a star and begin to heat up, ice on their surfaces sublimate, transition directly from solid to gas without becoming liquid. This outgassing creates pressure, tiny jets of material that act like natural rocket engines, pushing the comet in directions that pure gravity alone cannot explain. Astronomers call these non-gravitational accelerations, and they're well documented, they're expected, they're normal. But the non-gravitational forces acting on 3I Atlas don't match the pattern. According to Loeb's calculations, if the object were experiencing standard cometary outgassing, it would need to have a mass of approximately 33 billion tons to match its observed trajectory. For context, this would make it far more massive than any comet of comparable size we've ever studied. The Hubble Space Telescope estimated that 3I Atlas's nucleus, the solid icy core at the center of the comet, is somewhere between 0.32 and 5.6 kilometers in diameter. Most likely, it's less than 1 kilometer across. An object that's small should not have the mass Loeb's calculations require, unless it's made of something far denser than ice and rock, unless the standard model of cometary composition doesn't apply, unless something else is going on. Loeb has been careful not to jump to conclusions. He emphasizes that 3I Atlas is most likely natural, a phrase that appears repeatedly in his public statements. But he also insists that scientists must remain open to possibilities that extend beyond conventional physics. In his framework, this doesn't mean immediately concluding that 3I Atlas is an alien spacecraft, though he doesn't rule it out entirely. It means acknowledging that our models might be incomplete, that interstellar objects might behave in ways we haven't anticipated, that the universe might still have surprises in store. Other scientists are more skeptical. They point out that cometary outgassing is complex and poorly understood, especially for objects that have been frozen for billions of years in interstellar space. They note that small changes in the object's spin rate, surface composition, or internal structure could produce unexpected accelerations. They argue that invoking unknown forces is premature when more mundane explanations remain plausible. But the debate itself is significant. The fact that a tenured professor at one of the world's leading universities is publicly discussing the possibility of non-gravitational forces, forces that might involve unknown physical mechanisms, or even artificial propulsion, reveals how deeply 3I Atlas has challenged scientific consensus. This is not fringe speculation. This is mainstream science confronting data that doesn't fit, the color that should not be. When 3I Atlas was first observed in early July, astronomers noted its color and brightness. By August, something had changed. The comet appeared to be brightening rapidly, growing more active as it approached the sun. This was expected. What was not expected was the color shift. By late October, as the comet made its closest approach to the sun at a distance of approximately 126 million miles, observers noticed something strange. The comet had developed a bluish hue. Comets are typically not blue. They're usually white or yellowish, sometimes with hints of green from the glow of cyanide and carbon gases in their comas. Blue comets are rare, and when they do occur, the coloration is usually subtle and short-lived. But 3I Atlas turned distinctly blue, and it stayed blue, and then it changed color again. By early November, after passing behind the sun from Earth's perspective, the comet had shifted colors for a third time. Color in astronomical objects tells us about chemistry. Different molecules absorb and emit light at different wavelengths, creating distinctive spectral signatures that act like fingerprints. When a comet turns blue, it usually means something unusual is happening with its composition or the processes occurring in its coma. The repeated color changes observed in 3I Atlas suggest that the comet's chemistry is unstable, shifting in response to the sun's heat in ways that standard cometary models struggle to explain. Adding to the mystery, observations by the Very Large Telescope in Chile detected nickel vapor in the comet's coma. This was surprising for several reasons. First, nickel is a metal, and metals typically require high temperatures to vaporize. Second, the nickel was detected when the comet was still nearly 4 times Earth's distance from the sun, where temperatures should be far too cold for metal vaporization. Third, the nickel appeared without corresponding amounts of iron, even though nickel and iron usually occur together in cosmic bodies. They're forged together in the hearts of dying stars and generally remain mixed in the debris that forms comets and asteroids. The presence of nickel without iron suggests an unknown chemical process, something that separates these elements or creates nickel through a mechanism we haven't identified. Researchers describe the discovery as super exciting, a rare moment when scientists encounter something that genuinely surprises them. But excitement is often accompanied by confusion. If we don't understand how nickel is being produced or released from 3I Atlas, what else don't we understand about this object? The James Webb Space Telescope turned its powerful infrared instruments toward the comet and detected unusually high levels of carbon dioxide compared to water vapor. Most comets we've studied have relatively balanced ratios of carbon dioxide to water, reflecting the composition of the primordial disk from which they formed. But 3I Atlas is carbon dioxide rich, suggesting it formed in a colder, more carbon-rich environment than the comets native to our solar system. This makes sense for an interstellar object. Different star systems have different chemical compositions based on their age and the supernovae that enrich their birth clouds with heavy elements. But the extreme nature of the carbon dioxide abundance is still puzzling. It hints at formation conditions very different from anything in our solar neighborhood. NASA's Neil Gehrels Swift Observatory detected hydroxyl gas, a chemical fingerprint of water, in the comet's coma. This was described as a major breakthrough, confirmation that despite its unusual chemistry, 3I Atlas contains water ice like other comets. But even this discovery came with caveats. The amount of water detected was lower than expected for a comet of this size and activity level, again suggesting that something about 3I Atlas's composition deviates from the norm. Color changes, nickel without iron, carbon dioxide in excess, water in deficit. Each observation adds another piece to a puzzle that refuses to resolve into a clear picture. The jet that points backward. In late August, the 2-meter twin telescope at the Teide Observatory in Spain's Canary Islands captured composite images of 3I/ATLAS using 159 separate exposures. These images revealed something stunning: a giant jet of gas and dust erupting from the comet's nucleus, shooting outward in a fan-shaped plume. Jets are common features of active comets. As ice sublimate on the sunlit side of the nucleus, the escaping gas carries dust particles with it, creating visible streams that can extend for thousands of kilometers. But the direction of 3I/ATLAS's jet was unusual. It appeared to be oriented toward the sun, not away from it. Typically, cometary jets point away from the sun, driven by solar heating and radiation pressure. Physics dictates that material should be blown outward, pushed by the solar wind and the pressure of sunlight itself. Yet here was a jet, apparently defying this expectation, shooting material sunward. Scientists were quick to point out that this is not necessarily anomalous. Comets are rotating objects with irregular shapes, and jets can erupt from specific active areas on the surface that happen to be oriented in any direction depending on the comet's rotation. Additionally, the images showed the jet from a particular angle. What appears to point toward the sun from Earth's perspective might actually be oriented differently in three-dimensional space. But the sight was still striking, another example of 3I Atlas behaving in ways that capture attention and demand explanation. The jet's existence confirmed that 3I Atlas is indeed an active comet, not an inert rock or asteroid. This settled one early debate. When the object was first discovered, some observers reported no cometary features, leading to uncertainty about its classification. But by early July, multiple observatories had confirmed a faint coma and possible tail, and the designation as a comet became official. The August images of the active jet removed any remaining doubt. Yet the vigor of the outgassing raised new questions. For an object that had spent billions of years in the deep freeze of interstellar space, experiencing temperatures barely above absolute zero, 3I/ATLAS was surprisingly active. This suggests that its interior is rich in volatile ices that readily sublimate when heated. But it also means the comet is losing mass rapidly. Each close approach to a star would strip away layers of material, gradually eroding the nucleus. How many such passages has 3IATLAS survived? How much mass has it lost? And how much longer will it remain active before it becomes a dead, inert remnant?